Having introduced the general properties of waves, let's see how we can solve wave propagation, and what we'll use is the wave equation. So what we'll learn here is how the wave equation relates displacement, speed, and acceleration in a wave. And we'll learn how to apply it to determine the properties of wave, or the properties of the medium in which waves propagate. As we'll see, the velocity of a wave is actually dependent on what the wave is propagating in. So the wave equation is a way for us to give a mathematical description of the behavior of waves. And for simplicity, again, we'll consider a transverse wave propagating along a string. And what we can do is we can derive the motion using Newton's second law to a small element of the spring. We're actually not going to do this. I'm just going to show you the wave equation itself. But the approach is similar to what we did for simple harmonic motion, except that now, again, we have displacement not only in time, but also in space. The vertical displacement is also dependent on space, not just on time. So if we take a look at our element of a string or a rope, where we have a pulse coming through, and here x is our coordinate along the string or the rope, and z is our transfer displacement. We saw that z is a function of both x and time. And the assumption in the wave equation is that the displacement in z, the actual oscillation, is fairly small. So these angles are small, so we can use things like the small angle approximation. And they also do not change very quickly with x. So then the wave equation itself has this form. And so the second derivative of z with respect to time equals the ratio of T over mu. This is the tension in the string. This is the linear mass density of the string, times the second derivative of the vertical displacement with respect to x. And we'll also see that T over mu is actually the square of the transverse velocity of the wave. So what this is telling us is that the acceleration, this is vertical acceleration, second derivative of z with respect to time. The acceleration of the string vertically is proportional to the square of the wave velocity, so that the faster the wave speed, the faster wave propagates through our medium, the higher the vertical acceleration can be, and the curvature of the string. This is what the second derivative of z with respect to x is the curvature of the string. So here, for example, at the top, the string has the highest curvature, and here the curvature is 0, because this is now an inflection point. So for example, the wave equation will tell us that right away, if the curvature here is 0, the acceleration here is 0. There's actually no change in velocity at this point. The velocity actually happens to be, the vertical velocity happens to be at its maximum. Here, on the other hand, the curvature is the largest and it's negative. So this is telling us now that the acceleration is going to be the largest and negative, the acceleration in the vertical direction again. And we know this from simple harmonic motion, that when we're at one extreme, we have the largest acceleration, even though the vertical velocity may be 0 in that case. So that's what the wave equation tells us. So in this case here, for a string, the velocity is the square root of the tension of the string over the linear mass density. So this is the mass per unit length, mu, for the string. And what the wave equation does is it describes the propagation of small amplitude waves in any one-dimensional medium. So let's apply the wave equation in an example. Let's take a general expression for a wave, a transverse wave. So z is the transverse displacement along x and time. So this is our general expression for a transverse wave, where now we have also added a phase, an unknown phase, and let's demonstrate that this actually satisfies the wave equation. So we'll do this by just plugging this into the wave equation, so then taking the second derivative of z with respect to time and respect to x. This was our wave equation from the previous slide. So let's just put in the derivatives, calculate them, and check. So we do the second derivative of z with respect to time first, this being the acceleration. So here I've already taken the first derivative, and there's one more derivative with respect to time to take. And the first derivative, we know, for example, of the cosine is minus sine, so there should be a minus sign in front. But there's also, we're taking the first derivative of minus omega t, which will be minus omega, so there will be a factor of minus omega coming, which will cancel the initial minus sign. So then the first derivative of z with respect to t is actually just a omega sine kx minus omega t plus 5. But we still have to take one more derivative. So now again, the first derivative of sine is cos, and then we're taking a derivative with respect to time, so we have another factor of minus omega coming out front. So then the second derivative of z with respect to time is minus a omega squared cosine kx minus omega t plus phi, which actually is very similar to our starting expression. It's just minus omega squared z. This is our vertical acceleration. It's minus omega squared z. Now, if we take similarly the derivative with respect to x for z, the second derivative, we do the same steps, and we arrive at an expression where the second derivative of z with respect to x is minus k squared, k being the wave number, times z, and k being the wave number, this is minus omega squared over v squared z. So again, we see these two expressions are very similar, they just differ by a factor of this v squared. So indeed, we have demonstrated that this expression satisfies the wave equation, because the second derivative of z with respect to time is v squared times the second derivative of z with respect to x. So in fact, any disturbance of this form will satisfy the wave equation. That's worth checking yourself. And depending on what the medium is through which the wave is propagating, we'll have a different velocity. So in general, the velocity is omega over k, the angular frequency over the wave number. And for a string, the velocity is the square root of the tension in the string over the mass density of the string. So t is the tension, mu is the linear mass density, so the mass per unit length of the string. If we have a different kind of medium, the wave speed will always be proportional to something that describes how stiff your medium is. The stiffer the medium, the faster the wave propagation. The looser the medium is, the slower the waves will propagate. So for example, if you have gas, the wave speed again, omega over k, now is going to be equal to the square root of gamma times the pressure over the density. So it's proportional to the pressure in the gas. The higher the pressure, the faster the wave. And it's inverse to the square root of pressure, I should say, and it's inversely proportional to the square root of the gas volume density of the gas. So the lower density of the gas is, again, the faster the wave. So let's take another example. But now let's consider wave propagating in a solid, steel. So the speed of sound in steel is given by the square root of y over rho, or y is called the Young's modulus. It's this measure of the stiffness of the steel, and it's measured in newtons per meter squared. So for steel, it's 2.1 times 10 to the 11 newtons per meter squared. And this is a density, 7.9 times 10 to the 3 kilograms per meter cubed. So here's our situation. We actually have an underwater cable and a scuba diver inspecting it, and this goes to it's an underwater pipe. So there's a scuba diver inspecting it. The scuba diver wants to send a signal to a platform that's 5 kilometers away from this pipe. So the scuba diver has an option of using some sort of disturbance, whether it's to knock on the steel pipe or to try to propagate the message through water over 5 kilometers, which is of course impractical, but you'll see that the steel pipe actually is a practical way to convey that message. So the scuba diver can try to tap on the steel pipe to convey the message. And the question is can the message of tapping reach the platform that's 5 kilometers away in 1 second? So let's solve for this. The propagation speed of the wave, square root of the Young's modulus over density. Here are the numbers that we have given in the problem. So then the propagation speed of the wave is 5,200 meters per second. So 5.2 kilometers per second. For comparison, the propagation speed of sound in air is only about 300 meters per second. So this, you can see that in steel, which is a much stiffer material, the propagation speed is greater. So now the message will take 5 kilometers, the distance over the velocity, which is this. So it'll take 0.97 seconds to reach the platform, which is just under that 1 second limit that we were given in the problem. So the message will reach in time. Here's another example. We have a rope that's stretched between two supports that are 18.2 meters apart. And the tension in the rope is 78.6 newtons. And we are asked that if one end of the rope is jerked, then the disturbance reaches the other end just over half a second later. And the question now is, what is the mass of the rope? So we're given the tension, the length, and the effectively the speed. So the wave velocity again is V equals square root of tension over linear mass density. So linear mass density is just mass divided by distance. We're given and we're trying to figure out what the mass is. We're given what the length of the rope is. But we actually can figure out what the speed is because we're given the length and the time that the signal reaches the other end of the rope. So the speed is also just the length over this time. So now what we have to do is to equate L over T to square root of T, L over small t to square root of capital T over mu. And that's what we do here below. So we just take the square of this because we have a square root. So V squared is going to be T over mu. Mu itself is just M over L. So T over mu is T over M over L. And this also equals the square of this. So L over T squared. So then we can rearrange and find that the mass is the tension times the time it takes for the propagation squared divided by the distance. So then we put in the numbers, we find that the rope actually weighs 1.5 kilograms. And here's a final example which asks you to investigate a transverse wave in some detail given some numbers. Find amplitude, period, frequency, wavelength, and so forth. And it can be all figured out from the numbers. And apply all the concepts that you have learned so far to do a sketch of the rope at 2 different times. Figure out if the wave is traveling left or right. And then, given the mass per unit length, find out what the tension in the rope is. And this example has been left unexplored, but should you have questions, you're certainly welcome to ask these during office hours.